Hi, welcome to Fundamentals Friday. Today we're going to take a look at how transistors work, not at the circuit design level, but more at the physics silicon level. Let's go. Now, we're going to take a look at two different types of transistors because they are physically different in how they operate at the silicon level. One is the bipolar junction transistor, your BJT. The other is your field effect transistor, or FET. Now, we're actually going to look at a particular type of FET, the MOSFET in this case, because there are many different types, and well, that's probably best left to a different video. Now, regardless of whether you have a BJT type or a MOSFET, they're going to work in your circuit configuration pretty much exactly the same. We're going to look at the NPN type and the N-channel type only here today, and you should be familiar with these at the circuit level. If you put a positive voltage on the base, then you're going to get current flowing through your base emitter junction there. It's going to turn your transistor on, and your output voltage here is going to go to 0 volts. It's going to be pulled down, and if you don't have any base current, then it's going to go positive. By nature of the pull-up resistor, the transistor is going to turn off. So it's acting as a basic switch. And your MOSFET, in particular an enhancement mode MOSFET, which I might go into a different video on, if you put a positive voltage on the gate here, it's a voltage-driven device as opposed to a current-driven device in your BJT. So they are physically different beasts. But if you put a positive voltage on your gate here, it does exactly the same thing. It turns your transistor on and your output voltage goes down. If you ground your gate like that, then by nature of that, you're going to turn your transistor off, and your pull-up is going to take your output voltage high. It works like a switch exactly the same way as the BJT. But transistors can be also used as amplifiers as well. That's their other job. So you can put your sine wave in here and get a much bigger sine wave out here. There's actually amplification involved, power amplification, not just voltage amplification. You can do the same thing on your MOSFET as well, but you've got to bias them right. So they can be used as switches or amplifiers, and there's different circuit configurations which we won't go into. What we want to look at is the physics level side of it, how it actually works on the silicon itself. To do that, we're going to have to go to atoms. So welcome to the world of atoms, and we won't go into deep detail, but it's just important to know what's happening here. Stick with me, not as complicated as you might think. Now, transistors, of course, and silicon chips made out of, ironically, silicon, as the name suggests. And silicon is a semiconductor, but on its own, it's not very useful. It's not an insulator, it's not a conductor, and it doesn't conduct very well at all. It's pretty useless on its own. So you have to do what's called doping the silicon, i.e. adding an impurity to it to make it more useful. And we can create two different types of doped silicon. We can create N-type and P-type. You've probably heard those before. NPN, PNP transistor, PN junction diode. That's what it stands for, N-type and P-type doped silicon. So in a nutshell, pun intended, the outer shell or the valence shell of a silicon atom contains 4 electrons like that. And you can join up silicon atoms like this into a big matrix. They actually form a very nice big matrix where potentially you can actually conduct current through, but as I said, on their own, not very good. But if you dope silicon with a little bit of phosphorus, phosphorus is a very similar atom, but it's got 5 electrons in its outer shell. So if we have a phosphorus atom in here, they actually join up and fit into the silicon matrix very nice, except because it's got 5 electrons here, there's 1 free electron. Beauty, that electron is free to float wherever it wants throughout the matrix. So bingo, we've got an extra electron that's free to go all the way through and conduct current with. But we also need a matching type called N-type. So what we can do is we can get the element boron, and we can dope the silicon material with a boron atom. A boron atom, very similar, but it contains only 3 electrons in its outer valence shell here. So when it fits into the matrix of the silicon like this, it's doped in there, then there's only 3 electrons like that instead of the 5 that we had here. So 4 of them joined up and we had 1 free. In this case, we've only got 3, and there's what's called a hole left over. There's a space where there is no electron, so we've actually created a free hole, and that hole is then also allowed to move throughout the matrix, and that's what we can use to conduct the current through a PN junction through a transistor. Let's take a look. Now they call it N-type for negative because it's got an electron in, a free electron in there, and they ironically call P-type the positive type. But these names are a bit of a misnomer because the material itself is still a neutral charge because it's got the same number of protons and neutrons in the atom itself. So it's actually a neutral charge, but it's the hole, the free hole, that actually conducts the current through the material. So a hole in a P-type matrix here is just really the absence of an electron, but in semiconductor materials you can think of both the holes and the free electrons as being the charge carriers through the material, as opposed to just a regular metal where it's pretty much just the electrons that are actually carrying the charge current. Semiconductors, it's a bit of a different story. I won't go into deep detail, but just think the holes can actually move as well and carry the charge current. So let's first take a look at the BJT. Now, I've shown it stacked in this configuration. Actually, when you actually physically build up on a semiconductor in what's called a planar format, which is how I've shown this MOSFET here, when you physically build it up, it's actually physically tipped over, but it's easy to explain in this orientation. Stick with me. Now, we've got our base, our emitter, and our collector of our BJT transistor. And you'll notice here it is, base, collector, emitter down here. And we've got two N-type materials here, which are what's called heavily doped we saw before. So very heavily doped material, so very low resistance, you can think of it that way. Now, then it's got a P-type doped material in here that's electrically connected to the base. And then on top of that, we've got a sandwich between our base P-type and our collector N-type is another N-type, but it's like lightly doped, and we'll see the reason for that in a minute. So you can think of that lightly doped region, still N-type, but it's a bit higher resistance. So there's a higher resistance layer and a lower resistance layer on top of it. Now you'll notice that in a BJT transistor, we've just got a PN junction like that. Here's the two electrical contacts, P and N. It's exactly like a diode. That's why it's actually drawn like a diode there, and you can actually use a transistor as a regular PN junction diode. No problems at all. It functions the same way, and this is how it works. If we don't apply any voltage to the base here at all, we just put these two materials, physically sandwich them together, then what we end up with is all the free electrons in the N-type material, they actually gather and fill the holes on that side, and then the holes from the P-type material, which will show as positive here because the holes are effectively positive, right? Then they form on this side. So the electrons and the holes naturally gravitate towards the barrier here, and they swap polarity effectively like that, forming what's called a depletion region. In this case, because it's the base emitter, it's the base emitter depletion region. And the depletion region is actually effectively just like now a lack of any charge carriers. It's a barrier that stops any current flowing through your PN material from your base to your emitter. So basically, nothing conducts if there's no positive voltage on the base here, and you're familiar with that in how your basic transistor circuits work. Now, of course, we come to our typical diode curve here, which you should be familiar with. Once we get to about 0.6 volts is the threshold voltage, it doesn't conduct any current until we get to around about that point. And then once we get above 0.6 volts, it starts to rapidly conduct up like that. So as the base emitter voltage rises like this and goes up like this, the depletion region in here gets narrower and narrower and narrower until it flips back and overcomes the effectively like the threshold voltage here. Once it gets to 0.6 volts, then it flips back. Then we can start getting our electron flow. Here's our little electrons. They start flowing in that direction like that. Remember, electron flow goes from negative to positive. That's electron current flow as opposed to conventional current flow. So that's our base emitter junction. We haven't done anything with our collector yet. It's just been sitting there unconnected. Let's now connect it up, or let's not actually. When it's unconnected, the same thing happens. We've got a P and an N junction here because it's lightly doped or heavily doped. Doesn't really matter. We get exactly the same thing here. We get our negative electrons there and our positive holes building up on this side, and we get a collector base depletion region. Exactly the same thing. So no current flows from collector to emitter because there's that depletion region. No current can flow through it. It's effectively stopping it. But if our collector voltage here goes up and reaches a certain threshold, while our base emitter is also biased, then we get the depletion range, you're getting depletion layer in collector base, getting smaller and smaller and smaller, and then it flips over and bingo, we can now get, boom, electron flow from emitter through to your collector. Now, here's the magic of how a transistor works and how we get the current gain that we are used to. Like a small amount of base current here can lead to a large collector emitter current here. So it actually works as an amplifier. How does that work at the physics level? Well, let's take a look. Assume that our base is positively biased like that. Our collector is now positively biased at some large voltage. Now, this is where our heavy and our light doped material comes in. The lightly doped material, because it's effectively higher resistance. So because we've got a low resistance material here and a high resistance material here, which is going to be a very thin layer, by the way, this lightly, much thinner than what I've shown here. This is low resistance, this is effectively high resistance. So the voltage between the collector and the base here, most of it is going to be dropped. There's going to be a higher voltage differential in this lightly doped material, i.e. right in the region between the P and the lightly doped N-type material. And because that has a high voltage threshold, something magical happens. And the magic goes like this. There's going to be holes that are, so holes are positive, they're going to be flowing through the P-type material in like this, and electrons are going to be flowing the other way. It's going to be a small amount of current, but because this is all this N-type material at the bottom is so heavily doped, it's got all these excess electrons, and there's only a few little holes flowing through like this. When electrons flow from the N material, so electrons flow from here up into here, there's millions of them, but there's only like a few of the holes coming over. So where do the rest of all these excess electrons from this heavily doped N-type material go? Well, they go, bingo, straight up like that, because this is a higher potential differential voltage in this region here. It attracts all of those electrons, those excess electrons. So we've got a lot of electrons flowing from emitter to collector here, and just a smaller amount, much fewer electrons flowing from emitter to base. So bingo, that's how the magic happens inside a transistor, and you get current gain, a large amount of current from emitter to collector, or if you want to think about it in conventional current terms, the current flows from collector down to emitter, and a small amount, so a small amount of base current flowing in here, and a super large amount of current flowing from collector through to emitter, and that's determined by the beta or the gain of the transistor. And that's how and that gain is controlled by like all the physical construction of the lightly doped material and how thin it is and all that sort of stuff, the physical construction inside the transistor. So that's the magic of a bipolar junction transistor. Let's move on now to our MOSFET, in particular a MOSFET, not a JFET or a depletion mode MOSFET, for example. This is going to be what's called an enhancement mode MOSFET, how it actually works. Now, it's physically constructed quite different and operates quite different. As I said, this one is a current controlled device. You've got to actually feed some base current in. As you might know, a FET or a MOSFET, be it a J, whatever type of FET it is basically a voltage driven device. You put a voltage on the gate and you can get current to flow in the transistor. There is effectively no gate current, a voltage controlled device. So the way the MOSFET works in what's called a planar form here, this is how it's physically constructed on the silicon. We've got a p-type substrate base, it's of course p-type doped, and then we've got our two n-typed dope. You can think of them as like a physical channel or whatever. It doesn't really matter how you physically think of them, but there's two n-type nodes here. So the one is the source and one is the drain. And then we've got an insulator on top here, and that's usually like an oxide layer. There's a few different ways to do that, but just think it like a complete insulating layer. That's why it's physically shown as, you know, there is no direct electrical connection between the gate and the drain or the source, because it is completely insulated. And then on top of that, they've just got a metal contact, which is your gate material, and there's also a metal contact on the drain and the source N-type materials as well. So apart from that physical difference of no electrical contact whatsoever, it kind of starts to work in a similar way. Let's have a look. Because we've got an N and a P-type material, if we've got nothing connected, no voltages connected, the transistor's just sitting there, then exactly the same thing happens here. Our electrons gather in this material, and our holes from our P-type gather on the other side, and we form our depletion region in there around both of those. So obviously, if we've got two depletion layers here and here, then no current can flow from source to drain, i.e. the transistor is switched off. There's no conduction at all. But here's the magic of how it works, and the name gives it away, field effect transistor. It works based on an electric field. Now, if we put a positive voltage on the gate here, it doesn't have to be very high, like a couple of volts, depends on the type of transistor, then what we've done here is we've given it enough electric field here to overcome this barrier here, our depletion region barrier, and then we can have the electrons that were in the N-type material here, that's heavily doped N-type material, can actually flow along here, because this whole gate is like the whole thing is directly across there between overlapping the two N-type materials. It forms a channel in there where the electrons can flow, and bingo, we've turned on our switch based on just an electric field here. There is no current flowing in or out of the gate because of this oxide insulating here. So it is a field effect device turned on and off by an electric field or a voltage on the gate. And naturally, the higher the gate voltage, the more you increase that gate voltage there, then the wider this channel becomes, and you can get more charge carriers flowing through, holes and electrons, and current flow from your source to your drain, like that, and your transistor turns on. Bingo! Very, very simple, but as I showed, it's physically a different type of operation to the BJT type transistor. And because there is no gate current flowing in there, it's insulated. Well, that's usually an advantage in electronics. That's why MOSFETs are more popular than BJTs these days for most things. So yeah, your iPhone or whatever, all your processing, all your digital switching, all that sort of stuff is all done with effectively enhancement mode MOSFETs, exactly like we see here. And here's an interesting little animation I got from Wikimedia Commons. You can see the graph on the left here, that's the gate voltage going up to 0.6 volts. And you can see the black marker, it starts off at 0 there, goes up, and you can see the channel effectively turning on in this electron density map on the right-hand side. This is a 3D electron density map. It's awesome. I don't know how they actually got this, but it's fantastic. And you see, as it goes up and reaches a threshold voltage, in this case of about 0.45 volts or thereabouts. This is a real low gate threshold voltage nanowire MOSFET, it's called. And you can see the electron channel then just sort of bang, there it goes. Fantastic. And of course, you keep increasing the gate voltage, as I said, then your conduction channel gets wider and wider, and more electrons can flow, higher current. And you may have heard that MOSFETs and CMOS devices, complementary metal oxide semiconductor transistors, they're susceptible to static electricity. If you touch the pins, you can zap them and destroy or damage the chip. How does that happen? Well, it's easy. This very thin insulating oxide layer in here, that's what gets damaged. If you come in with your finger and touch your gate in there, zap, you can zap straight through that insulator, actually blow a hole in that insulating layer, and that's going to ruin your day, really. And these insulating layers, incredibly thin. We're talking like, nanometers, kind of thickness in there with these things. Incredibly tiny. Now, you may have heard of Moore's Law, of course, and how chips and transistors, these types of MOSFETs, which are used to build modern processors and modern chips, are getting smaller and smaller and smaller. A current process node or manufacturing node technology, you might have heard, for example, 20 nanometers. What does that mean? Well, it means the distance between here and here, this channel in there, that is your 20 nanometers in there. What does that translate to? Well, a silicon atom is about 0.25 nanometers in diameter, effectively. So there's effectively only 80 atoms in there, wide between there. So you can see how ridiculously small feature sizes these are, and how Moore's Law, as we traditionally think of it, is pretty much coming to an end. You can't get much smaller before this doesn't become an insulator anymore. It doesn't become a barrier. The electrons will just jump across and they can tunnel through. You can get we get to the point where quantum effects and quantum tunneling comes into it. I won't go into the details of that, but yeah, we're really sort of pushing the limits of Moore's Law. We can't physically make these much smaller before we run into lots of real major problems. And these distances in here, and also the thickness of the oxide insulating layer in there, determine your operating voltages of your FET. So you may have heard of like a 20 volt maximum FET, for example. Well, that's going to be determined by your particular manufacturing technology inside the FET itself. That's going to determine your maximum operating voltages. So there you go. That's how BJTs and MOSFETs work at the semiconductor level itself. And I hope I've explained that adequately. There are sort of many different ways to sort of explain this, and you can go into real deep into the physics and the manufacturing technology of it. This is just a general overview, good enough. If you know this, then you pretty much know how these and can appreciate how these transistors actually work on the silicon level. And I've only covered NPN and N-channel devices here, but you can think of PNPs and P-channel MOSFETs as being basically the opposite of what's here. It's not quite, they do operate a bit differently. They have negative gate voltages, for example, but JFET N-types can have negative gate voltage as well, and I could probably do a separate video on that, but there are physical differences and also operational and parametric differences between PNPs and P-channel and N-channel devices. So, but pretty much it's basically the opposite of what we got here. So if you like Fundamentals Friday, please give it a big thumbs up on YouTube, because that helps a lot. And if you want to discuss it, jump on over to the EEVblog forum, links down below, or leave YouTube comments or blog comments. Catch you next time.